Hello students. So what happens if we try the same thing with notes, but notes either have to last for 2 or 3 beats? So for example, if I have, let's say 2 total beats, I could just have, let's say, a medium. With 3 beats, I could have a long. With 4 beats, I could have 2 mediums. Say a medium is a 2-beat note and a long is a 3-beat note. And what about for 5? Well, I could have a medium and a long, or a long and a medium. For 1, nothing. No way to do 1 beat. But for 0, we could just not include any notes. And then we have 1 way. So I get 1, 0, 1, 1, 1, 2. Let's do a few more. 6, 7, and 8. Okay. So for 6, well, I could do 3 mediums or 2 longs. For 7, I could go medium, medium, long. Not drawn to scale. Medium, long, medium, or long, medium, medium. So 2, 3. So I'm getting some sequence here, and that's enough drawing for right now. My sequence goes 1, 0, 1, 1, 1, 2, 2, 3. How can I figure this out in general? Well, if I have a total of n beats, I have to either end with a medium, which would mean I have n minus 2 beats to fill, or I could end with a long, which would mean I have n minus 3 beats to fill here. So that tells me if I make a sequence, Pn, it's going to be equal to Pn minus 2 plus Pn minus 3. This represents the total number of ways that I can make a rhythm that ends with a medium, and this the total number of ways that I can make a rhythm which ends with a long. And together with my initial conditions, which is P of 0 equals 1, P of 1 equals 0, P of 2 equals 1, this should be all I need in order to compute the sequence. And there's many, many ways to compute the sequence, but we are going to use generating functions. Okay, so let's try this out. So what I'm going to do is I'll let P of x be my generating function, and it's going to be the sum of each of the Pn's times x to the n. And I need to go a little further out before I can use my relation. I'm going to need to go out to term 3, because my relation is that P of n equals P of n minus 2 plus P of n minus 3. But if I go out to term 3, that's fine because term 0 is defined. So I'm going to get P of 0, x to the 0, plus P of 1, x to the 1, plus P of 2, x squared. And now I get this, starting at 3, P of n, x to the n. Okay, so I can use my identity, and I know what these are, and you know what, I'm just going to plug them in. Will I? Sure, I'll just plug them in. We'll save some space. So this is 1, 0, 1. So this is going to be 1 times 1, nothing here, and then plus x squared. Okay. And now, for this, I can use my identity. I'm going to get Pn minus 2 plus Pn minus 3 x to the n, which gives me this. Okay. So there's a lot of different things that I can do. The question is, what do I want to take care of first? What's upsetting me? Well, I want these to match, I want these to match, I want these to start at 0, and I want these to start at n. I want all of those different things to happen. And it honestly, you don't have to do them in a certain order. Maybe some orders tend to be a little easier than others. I guess what I'm going to do is I'm going to start these at n. So let's get this to p of n, and p sub n, and this to p sub n. That's usually a nice one to go with. So I'm going to re-index this by replacing n with n plus 2. And this one here, I'm going to re-index by replacing n with n plus 3. Okay. So now what can I do? Well, oh, sorry, n plus 3. Forgot to write the n plus. Okay, so now what can I do? Well, I can pull out an x squared, and an x cubed. I could have saved that for a later step, but whatever. And I like how this is looking. This is very nice. I like how this is looking except for the 1, so I'm going to use my adding 0 trick. What I'm going to do is I'm going to subtract off the first term. Remember, this is times x squared, so each of these terms are times x squared, so I'm going to subtract an x squared p naught x to the 0. And that allows me to just start this at 0. And you know what? I can't even wait. I'm going to write that as p of x right off the bat because I know that's what that is. Okay. And now that cancels because this is just a 1. So I'm going to get a 1 plus x squared p of x plus x cubed p of x. And this is equal to p of x still because all of this started with p of x. So I move all my p's to one side, and I'm going to get this. 1 minus x squared minus x cubed equal to 1, or this right here. And that is my generating function. Now, you might think that since I like Pingala, that I was naming this after him. No, this is actually the Padovan sequence, which was not created by Padovan. It was discovered by Hans van der Laan. Also, like many things in math, not appropriately named. But in any case, the P here is for the Padovan sequence, and that's what these numbers are commonly called. Some people like to start the Padovan sequence at different places. In this situation, I started it at 1, 0, 1, 1, and so on, because I was counting it directly from rhythms. But it also appears out of spirals and all sorts of different things. And of course, you can adjust this using multiplication by x to the n, and maybe adding on some terms if you need to in order to make things work out, in order to make your initial conditions fit whatever you want your initial conditions to be. But that's a nice second example of solving a recurrence relation using generating functions.